Welcome to bubble sort. Bubble sort is one of the simplest sorting algorithms. It repeatedly compares two adjacent elements. If the left element is greater than the right, they are swapped. After each full pass through the array, the largest unsorted element moves to its correct position at the end. This process repeats until the entire array is sorted. Let's watch it in action. Starting pass 1. Comparing 74 and 23. 74 is greater than 23, so we swap. Swapped elements at positions 0 and 1. Comparing 74 and 82. 74 is not greater, no swap needed. Comparing 82 and 14. 82 is greater than 14, so we swap. Swapped elements at positions 2 and 3. Comparing 82 and 67. 82 is greater than 67, so we swap. Swapped elements at positions 3 and 4. Element is now in its final sorted position. Starting pass 2. Comparing 23 and 74. 23 is not greater, no swap needed. Comparing 74 and 14. 74 is greater than 14, so we swap. Swapped elements at positions 1 and 2. Comparing 74 and 67. 74 is greater than 67, so we swap. Swapped elements at positions 2 and 3. Element is now in its final sorted position. Starting pass 3. Comparing 23 and 14. 23 is greater than 14, so we swap. Swapped elements at positions 0 and 1. Comparing 23 and 67. 23 is not greater, no swap needed. Element is now in its final sorted position. Starting pass 4. Comparing 14 and 23. 14 is not greater, no swap needed. Element is now in its final sorted position. Elements sorted and locked in place. Element is now in its final sorted position. Congratulations! You have successfully completed the bubble sort lesson. Let's review what happened. The algorithm sorted the array in 4 passes. It made 10 comparisons each time it checked whether two adjacent elements were in the right order. It performed 6 swaps each time it had to move a larger element past a smaller one. The original array was 74, 23, 82, 14, 67. After sorting, the array became 14, 23, 67, 74, 82. Here are the key takeaways from this lesson. First, bubble sort works by comparing adjacent elements and bubbling the largest unsorted value to its final position with each pass. Second, after every pass, the sorted boundary grows by 1 element, so the algorithm needs at most n-1 passes to fully sort an array of n elements. Third, in the worst case, the time complexity is order n squared. This happens when the array is sorted in reverse order. Fourth, the space complexity is order 1. It sorts entirely in place using only a few temporary variables, requiring no extra memory. Interesting insight, 6 swaps out of a maximum of 10 a typical average case run. Now let's explore the time and space complexity of bubble sort in detail. Best case O, n. This occurs when the input array is already sorted. Bubble sort detects this in a single pass with 0 swaps, making it very efficient for nearly sorted data. Average case order n squared. For a randomly ordered array, Approximately n squared over 4 comparisons and n squared over 4 swaps are needed on average. Worst case order n squared. This happens when the array is sorted in reverse order. Every single comparison requires a swap, resulting in the maximum possible work. Space complexity order 1. Bubble sort is an in-place sorting algorithm. It only needs a few temporary variables regardless of the input size. No auxiliary arrays are created. When should you use bubble sort? Bubble sort works well for small or nearly sorted data sets, where its simplicity shines. It is also excellent for teaching sorting concepts because its behavior is easy to visualize step by step. When should you avoid bubble sort? Avoid bubble sort for large datasets above about 1000 elements where its order n squared time complexity becomes too slow. For production systems, prefer algorithms like timsort or introsort. That's everything about bubble sort. Well done on completing this lesson.